So, ladies and gentlemen, welcome back to the afternoon session of Hacktivity 2021. Our first speaker this afternoon is Piotr Głaska, and after his presentation, there will of course be time for some questions, should you have them. Thank you. Piotr.
Hi, good afternoon. As introduced, I'm Piotr. I'm working for Infoblox. It's a vendor of secure DNS solutions. I'm based in Warsaw, Poland, but very happy to be in Budapest today. So what I want to show you today is an overview of some interesting malware examples and APT attacks examples, which I have seen over a couple of years, not researched them by myself, but actually looking into them by myself, how they are using DNS. Because if we look at cyber kill chain, we can see that most of the malware somehow is using DNS on different phases of intrusion kill chain. So, you know, we have a reconnaissance phase. The attacker needs to get information about the victim's infrastructure, what kind of applications they are using, what kind of systems they are using. With DNS, they can get some information about IP infrastructure, what addressing they use. Sometimes you can get some information from TXT records, what kind of applications are used, and so on. Then they prepare the weapons, so prepare the code, prepare the infrastructure. If they will use some domain names, they need to register them, they need to set up DNS servers, and so on. Then we have delivery phase, where the malware is actually delivered. That could be attachment with an email. That could be email maybe with a link. This link usually would be delivered as a fully qualifying domain name or FQDN, right? So it needs to be resolved. It could be sent over LinkedIn message. You never know who tries to connect with you. Could be sent over Facebook, whatever, right? If this is a link, it needs to be resolved, and then also defenders have some first possibility to react. If this is malicious domain name, it's listed somewhere, then it could be blocked. Then we have next phase, exploitation of vulnerabilities. In terms of DNS, that could be software vulnerabilities in DNS server or in DNS client. I will not show you today because we have not enough time. But last year, there were a lot of vulnerabilities in DNS clients, especially IoT devices, such as Ripple20, for example, and also a couple of interesting server-side vulnerabilities, such as Secret in Microsoft DNS, for example. Then we have installation phase. DNS is not used here much, but the most interesting phase, I believe, is command and control, especially from DNS perspective. I think most of advanced techniques, how attackers use DNS, are in the C2 phase. Because first, attacker needs to have an IP address of the C2 server. That could be hard-coded in the malware. But then they risk that someone blocks this IP, and then the whole work they did before will be lost because they lose communication with the C2 server. So much more often we see that C2 address is delivered as a fully qualified domain name in about 80% of the malware. Sometimes we can see that attackers try to bypass some reputational-based system, which would block domain name based on the threat feed, with algorithms such as DGA, or domain generation algorithms, or some interesting cases of DGA, dictionary-based DGAs. Finally, when the attacker has an IP address of the C2 server, the whole communication could be also hidden inside of DNS replies and DNS queries. So basically, a query could contain information such as, I'm in and registering in the C2 server, what should I do next, right? Then the C2 server will send DNS reply, do this and that, right? Do screenshots, type voice recording, run a specific command, and so on. And finally, we have actions on objectives phase, where attacker tries to achieve what he actually wanted at the very beginning. So that could be requesting ransom, that could be denial of service, that could be stealing data. DNS, of course, is great protocol from the attacker's perspective to do denial of service attacks, but also it's a choice of advanced groups when they need to exfiltrate data, so leak the data from the victim's infrastructure to the C2 server, and they want to stay undetected for a very long period of time. Because Most of the vendors are focusing security systems on web traffic and mail traffic. So the most popular. But there is this third most popular protocol, which is DNS, and it's often overlooked. We start today with the last phase, actually. So attackers is in, and let's see how attacker can leak data out of the victim's infrastructure. High-level overview of this technique, very simple. Attacker needs to first register some domain name, such as, for example, here, company.pw, set up DNS servers, which are authoritative for this domain name. Then, from the infected host, doesn't have to be an endpoint, right? It could be server, virtual machine, instant in public cloud, a printer, IoT device, whatever. Infected host. On infected host, the data which will be sent out needs to be encoded, because data will be sent here in a fully qualified domain name in the query. So basically, it needs to comply requirements of RFCs, which say how FQDN can look like. It can have maximum 253 characters. It could have 63 characters between the dots, so in the DNS labels. And those characters could be letters, and this is case insensitive, digits, dash and underscore. So attacker needs to encode the data in a way which will be compliant with the RFC. Usually they use either hex encoding, especially in case of simple criminals, or base 64 encoding, because it's very easy to do. It's functions to encode the code base 64 are available in any scripting language. Or in case of advanced group, that usually would be base 32, sometimes with customized alphabet. After data is encoded, they need to cut it into the pieces, build individual DNS queries, and then those queries are sent to local DNS resolver. So a corporate, Microsoft DNS, Bind, or whatever company is using. Then this resolver looks at the query looks okay, RFC compliant, so it is resolved on the internet, which means it will reach the server responsible for company.pw. So the attacker's control server, the attacker gets the data, combines all the packets together, does decoding, and then he gets the data. Very important thing to note, the communication is not done directly from the infected host to DNS of the attacker, because it doesn't have to be done this way. DNS system, by design, works as a multi-hop proxy system. When you send a DNS query from the client to local resolver, this resolver is not just forwarding this packet further, but it creates a new packet with a source IP of his own IP, right? So the DNS server IP is replacing the IP of the client. And then this query is sent to next DNS server and next and so forth. So it's a multi-hop proxy. Even though this computer doesn't have direct internet connectivity, but if it will be allowed to send a DNS query to this resolver, and this resolver can resolve it, then basically we have a bidirectional communication between those two hosts done by the local DNS resolver. So sometimes people forget about it. For example, in energy networks, there are operational technology networks which are theoretically isolated from the internet. And if you do ping or whatever, you cannot connect to the internet. But often, in very simple tests, you do nslookup google.com and you get the answer, which means actually there was bidirectional communication. The query was sent to the internet, and the reply comes back to the system. So it's an important topic not to be forgotten in some testing. Let's, maybe before I show real case, let me show you some demo of this technique. We have a tool to do simple testing and to show the technique. We have some domain names registered, DNS server set up, and if I send some data over DNS, it will be received here. Right now we have no data, 0 entries. And there is also a script generator where I can select a file, for example, JPEG file from my laptop here, which I want to send to data to server in California. We have several example scripts here. You could do it, in this case, over Perl, Unix shell, PowerShell. Attacker can do it in whatever language he wants, right? As long as this language or scripting language allows him to read the data from the file, encode the data in some algorithm mentioned before, and send DNS queries. So it's very simple. If we look at the shell script, for example, I am doing presentation from macOS. The script is very simple. It's reading data with the hex dump command here. And then the hex encoded data is cut into the pieces and sent with the host command as a DNS query. So we use just two tools which are built into the any Linux, Unix or macOS machine. So it's leaf of the land. You don't need to upload any tools. You just use what's found on the victim's system. Then if we switch back to the transfer files, we should see the file here, getting received, almost finished. Now it's finished. And we have 153 bytes, chunks of data. And here it is. The file from my laptop was exfiltrated to a data center in US. So this is, in general, how this technique works. Data is encoded in the hostname part in this example. Then we have a query number, which is useful if we want to let's say, make sure the order of the data is correct. DNS queries usually go over UDP, so you need to make sure they will arrive correctly and so on. Usually, attacker will put a unique ID of this infected machine somewhere in the name because it is losing on the way of the query, the source IP of this machine is lost, right? So we need to differentiate between different hosts, so you need to somehow specify this inside of DNS query. Let's look at the real cases of malware. First, let's start with something simple. So simple criminal group trying to steal data from computers which have connected payment terminals. As we see, they build queries which are quite long, especially the second one, right? It's very long. So it's easy to detect it as at least suspicious because most of the queries have much smaller length, around 60 to 80 characters. Here we have much more. Let's try to decode this data, what they used. I need to switch back 1 second. Okay. We will use CyberChef tool, an excellent tool which can do a lot of encoding, decoding. So here it is the query. We need to remove the domain part because it does not contain data. If we look at this, normally first thing we would assume, definitely it's not a hex, right? We have case-sensitive characters here. Looks like base 64, so we can try base 64. It's not standard base 64 because then you have plus and slash. Here we don't have such characters, but we have dash and underscore. And there is a special URL save version of base 64 which contains dash and underscore as those special characters. Data is still not readable, at least not for humans. Very simple technique which is often used by attackers to obfuscate information would be an XOR function. So let's try XOR with the brute force. If we don't know the key, CyberChef will show us different results for different keys. Then we can scroll and see if we can see some information here. And for the AA key, actually, we can read the data. So what we see here is, here, unique ID of infected computer, a name of this computer, Donovan PC. Then we have a name of the process which is processing credit card information, POS-exe. Then we have a credit card number, expiry date, and some other details about credit card. So it's very simply encoded inside of the DNS query, which is really bad news for the victim because DNS queries, as they travel internet, they are not encrypted. even if someone is using DNS over HTTPS or TLS, the encryption is taking place only between the client and the first resolver. Then it is sent unencrypted further. So it always travels internet unencrypted. So if someone has access to passive DNS archives, let me show you one example from Infoblox passive DNS system. I can actually investigate this domain name and see if we can see any queries which were archived from DNS resolvers sent by some clients on the internet. And here we go, we have 10,000 different domain names, and we can even see them. For example, we see even today, someone is exfiltrating data using this domain name. So as we speak, someone is actually using that yesterday and so on. And here you have 10,000 credit card numbers. So basically, from this perspective, it's really not good for the victims. Let's move to a little bit more advanced attacker. Sunburst backdoor was deployed within 5hands ransomware campaign, which was done in December 2020. And basically, they did first stage of infection by using some, brute force against remote desktop servers, so trying different credentials. Or in next phases, they moved to using zero-day vulnerability in some VPN gateways. Later, after the first phase, they were using Sunburst backdoor to download more malicious modules to do, Active Directory reconnaissance and to basically what they wanted to do to finally deploy the ransomware module. To download these modules, they use Sunburst backdoor, which was communicating with C2 server over DNS. And here we have a screenshot, again from passive DNS, where we see a communication from December, so one day before Christmas Eve, and you see how they communicated. So you have hex-encoded data here, and then you have a bunch of different IPs. So for every query, you have different reply. The reason is that those IPs are basically not IPs. These are just chunks of 32-bit data which meant something to the infected host. So this is how a little bit more advanced attacker is using DNS. We see that it's much shorter, it's not a long query, and then use some advanced communication mechanisms inside. The most advanced case I've seen in last year, it's of course Sunburst. Everybody heard about it. It's related to SolarWinds breach. So basically, they first broke into the SolarWinds, and then with the updates to SolarWinds network management system, they delivered malware to something like 18,000 companies. In the first phase of infection, they did C2 communication over DNS. So after first infection, the infected host would send a DNS query to a specific domain, and inside of this query, there would be some information, such as, I'm in, the name of the internal domain name is like this one. On the system, there is, FireEye, CrowdStrike, or whatever is running there. So basically, this data was exfiltrated over DNS. Here we see how it was encoded. So the query was built like this one here, encoded data in the hostname part, then AppSync API EU West 1. So basically, it looks like AppSync functionality from Amazon. And then we have finally domain name avsvmcloud.com, also kind of lookalike domain name, which would impersonate AWS, right? Data encoded here, it was encoded with base 32 with custom alphabet. So usually when we see APT group, that's most likely what you would see. Base 32, but not standard one, RFC standard one, but custom characters used for that. In this encoded data, there was a unique identifier of this machine, which was infected, because again, we lose, as attacker is losing source IP of the infected machine. So this ID has to be in the query, and it was the case here as well. MAC, address name, and global unique identifier from Windows registry. Then 14 characters with internal domain name. because they infected, almost 20,000 companies, but they were not interested in all 20,000. They were interested just in the bunch of, ministries and some other important institutions. So they need to know where they are in, and they send this information inside of DNS query as an internal corporate domain name. If 14 characters would be not enough to say if you are interested or not, then C2 server would reply, so send DNS reply with an IP address, which would not be IP address, but it would mean, please send me next part of the domain name. Maybe again, please send me another part, until it finally can recognize if the domain is interesting or not. Also, quite interesting thing was that those IPs in reply, which were not IP addresses, in fact, but they were chosen from IP ranges of public cloud companies such as AWS, Microsoft Azure, Google Cloud, and so on. So if someone was looking at this communication without knowing what is it, he would see some encoded data looking like it's an AppSync functionality to AWS, and the IP addresses would be from AWS, so not much suspicious, right? Then they would ask, C2 server would send a reply saying, give me the security, status of security solutions running on the system. That would be sent again inside of DNS reply. Finally, if they are interested, the C2 reply would be moved to the next stage of infection. Then they would switch to C2 over HTTPS. I believe they choose C2 over DNS because if you infect 20,000 companies, so there is lots of traffic, so you need to stay really low to be undetected. If that would be lots of different strange HTTPS traffic, it's a little bit easier to detect. But not too many companies are monitoring DNS traffic, so it's much easier to stay undetected. Another interesting example, it's a very popular criminal group, TrickBot, very well known. They have a special version of TrickBot called Encore DNS, which is deployed when they infect some important computers such as Active Directory controller. Encore DNS, as name implies, uses C2 over DNS, and the reason is very simple. If they would do command and control over HTTPS from Active Directory controller, then basically it's easy to detect. Nobody is, or should not be, browsing internet from the AD controller, right? But on the other hand, most of AD controllers in companies, they have Microsoft DNS on it, and they are first resolver for any computer in the company. So this server is receiving a lot of queries, sending a lot of queries to different domain names in the internet, and getting a lot of replies from different places. So DNS traffic from unusual domain is normal. Everything is unusual then, right? So that's why for those premium customers, they choose to deploy Encore DNS and do command and control over DNS. And here we have example of the query encoded data. After simple XOR function, we can see name of the campaign, name of the host. Again, unique ID of infected client. It's always somewhere there. So just by looking in passive DNS system, threat researchers actually later can say, for example, how many computers were infected. Because you see that, well, not exactly, but at least you get an idea. Different technique used by the attackers during C2 communication is infiltration, or generally downloading modules onto the infected host. This also could be done over DNS. Here we have example of advanced group in Visimal. This was nicely described in ESET threat research report. So here the infected computer is sending DNS query with a hidden message to attacker control server, but indirectly through local, normal, legitimate DNS resolver. And then in the reply, in this example, either null record or quad A record, there would be some data which later could be used to build a whole malicious module. So parts of malicious components were downloaded inside DNS replies. In this case, they targeted military sector, which obviously have a lot of isolated network segments. Sometimes they are physically isolated, then of course this will not work. But sometimes these are less important networks which have just firewall and hosts are disconnected from internet, but often, again, the fact that DNS resolver can resolve internet domain names is overlooked. So that's why in such cases, in military sector, in banks, attackers often prefer to use C2 over DNS. Again, base 32 encoding with custom dictionary, so typical APT group behavior. Another example of similar technique, but in simple malware, it's a DNS messenger and a couple of others. Let me just show you this example. So in this case, a malware which wanted to download malicious code onto the system after the initial infection was asking about TXT record, for example, mail rel.info, and inside of TXT reply, basically there was malicious code. This malicious code was first zipped, then base64 encoded, cut it into 200 byte pieces, and put here as a $E variable. So later the infected host is getting this data, putting it as a $E variable, concatenated. Then in the same record we have instruction to do decoding of this $E variable. So do base64 decode, uncompress, and then basically IAX means invoke expression, so run the downloaded code. So also simple way how the malicious code, new malicious modules, for example, are delivered by the attackers to infected machines. Also quite interesting example, September last year we detected in customer traffic DNS queries which look like this one, those one here. And it was detected as a DNS tunneling. When we looked more into the malware sample, reverse engineered that, we saw that there is quite interesting way how to get C2 domain name. Typically, C2 domain name is hard-coded into the malware. But in this case, it was not. To get C2 domain name, malware would connect to legitimate services, cryptocurrency services, such as blockchain.info. It would ask for cryptocurrency transaction details, and inside of these details, there was a field encrypted with AES, and this field, after decryption, it was holding a domain name for command and control. So wherever they want to change domain name, because maybe this one will be blocked somewhere, just by reputation, then they have a very easy way to change this domain name. Just change details of the transaction, made another transaction, there is new domain name which malware can use. So it's important, if you block things on DNS server, don't focus just on blocking based on a static list or even, some kind of, downloaded list of malicious domain names, but also it's important to have some algorithms which will detect the technique itself, independent from the domain being used. So how we do that is, or basically how you can do that, it's, there are at least three possible ways. I mean, you could do that with signature-based detection, for example, on IPS. The problem is that signatures are always focused on specific malware or tool. So if attacker will change the code, the signature will be easily bypassed, right? So it's good to detect some known tools, some known malware, but it will be usually not effective against unknown new malware families. Or even known tools, but those which were slightly modified and obfuscated by the attacker. Then you can do that based on reputation of the domain name. So if the domain name has a bad reputation, then basically do not allow resolving it. But again, the problem is the same. It works if we know that this domain name is bad, right? If we don't know, then we won't be able to detect. So that's the problem with this approach. So the approach which is best is to focus on technique itself, independent of IOC, independent of how query is built. But you try to find that that DNS queries might possibly contain some data encoded. So this is how we do it. Basically, we have an algorithm on DNS server which is inspecting each and every query and checking dozens of attributes of those queries. Each attribute has a weight, And then after calculating all the score for all the attributes, assigning the weight, we have final score, which is saying this is probably data transmission, or maybe it's not data transmission, right? What we check is, for example, Engram distribution. So Engram is a sequence of n characters. So we take an FQDN, we take first 2 characters, and we check, are those 2 characters together typical in natural language or not? If we see AD letter together, two letters, AD, that's quite typical in almost every language. So you have words like Adam, administration, whatever, right? But if you see QX, not very typical in any language, right? So then we score a little bit higher, and we check next bigram. And again, and again, and again. Then we do the same and check 3 letters next to each other. Are they popular in natural language or not? And here you can see how it works. I mean the result. The green color, with the green color we have marked good domain names, legitimate ones, most popular ones, and in red we have a computer-generated domains generated by the malware. So you can easily differentiate between them, although it's not always perfect. You have a little bit of green here, which means you will have false positives if you use just this one attribute. So you need to use more. What we also calculate for every query is entropy of characters. Entropy is telling us how much data is inside of the string. Like if I have 10 A letters, the entropy is 0, because it's just 1 letter. But if I put AB, I already will have much higher entropy. If I do ABC, there are 3 different characters, so it's much more data, right? So the more different characters you have, the entropy will be higher. The entropy is also, as you see, not perfect. I mean, it's worse than Engram distribution, but you can have a limit here, and then you get nice results. Also, there will be false positives if you use just entropy, so you need to use more things, but it's also good to calculate it. Then we do a lexical analysis, like what's the ratio of non-letter characters? What's the number of digits in the whole domain name? What's the number of those special characters? Typically, domains do not have many digits, right? But if you use hex encoding or even base 64, you will have a lot of digits. We check what's the ratio of hexadecimal characters, A, B, C, D, E, F, because they also can mean probably there is a hex encoding here. Then we check vowel ratio. Domains are made for us, mostly for humans, so they usually are built from the words. If you look at the vowel ratio, for good domain names, typical ratio is between 18 to maybe 55%. Bad domains which are generated by the malware, so those which contain data inside, they basically have a vowel ratio lower than 18%. So it's also nice characteristics. Also, it's not ideal. Sometimes you have some false positives. Then we check, for example, Gini index, classification error, number of DNS labels, what's the frequency, is it low, is it high, is it variable or fixed, what's the size of the query, and so on. So after you check so many attributes, you have assigned different ways to them, then finally you get the right result that maybe in a month you will get 1 false positive or 2, and that's all. If you would just use entropy, that would be much, much higher number. So thanks to using different attributes, you get better result. Another technique, which is also one of advanced techniques, is DGA, and specifically dictionary DGA. Typical domain generation algorithm is working like that. After initial infection, malware, instead of connecting to hard-coded domain name, will generate domain name from random characters and try to resolve it. If the attacker will not register this domain name, the code will generate another one, hundreds per day, until they will finally generate, or malware will generate one which was registered by the attacker. Attacker knows the code, so he knows that this day, this 1,000 domain names will be generated, and he chooses just one, right? But this is quite simple to detect. You can use the same algorithm for DGA like we do for data exfiltration, and we do that. But the problem is, what if instead of random characters, they will choose random words? So the malware will contain 2 or 3 dictionaries, 100 words each, and will generate those domain names from those words. then these magic things like entropy, Engram distribution will not work, right? Here is example from Superbox. So you have domain names like facegun.net, walkroad, and so on. They look quite normal. So what we do is we observe DNS queries in long time, and we notice that basically if someone is using dictionary and generating a lot of domain names, those words from the dictionaries will be repeated. If malware is generating thousands of domain names, dictionary is 100 words. On average, every word will be repeated 10 times. So what we do is we build a graph of words of all the domain names we see. We split the domain names into words. This is actually language independent because it's not really on words, but on engrams. So it will work for any language. But generally, we split it into words. And if the word is repeated, like road here, it will be a connecting node in the graph. But if it's not repeated, like lift or walk, it will be a lift node. And if you build such graph for legitimate domain names, this will look like this one here. But for dictionary DJ malware, you will see something like that. Those black spaces are basically those words which were repeated, which means words from the dictionary. So even without having a malware sample, we can say what kind of dictionary this malware is using, and we can predict what kind of domain it will be using. So very interesting approach. So key takeaways from today's session. DNS, from the perspective of the attacker, is not only a method of resolving domain name into IP address. It could be, of course, but if they use it for C2, for data exfiltration, for them it's just a method of transmitting any kind of information. That could be, of course, C2 server address, but it could be task to execute, sensitive data, new malicious module, which should be downloaded on the infected host. Second, DNS resolvers, by design, work as a multi-hop proxy. So you have this technique in MITRE ATT&CK framework, right? Multi-hop proxy. With DNS, it's by default. You don't need to do anything. Second thing, just remember to look at the DNS traffic at your companies. At very minimum, you should archive DNS queries so you have a look in the past. For example, it was very useful with Sunburst, because then in the archive, you just check, has any of computers in my company asked for avsvmcloud.com? If yes, then I have a problem. If not, then I don't have a problem, right? So very simple check retrospectively. If you would like to test something with this tool which I shown earlier, just go to Infoblox Booth. We can give you access to it, and if you do such tests, then later you can also receive a nice power bank. So I encourage you to visit our booth on the left. From my side, that's all. We have 2 minutes, so maybe there are some questions. Don't be shy.
We do have time for a few questions. Anybody? Ah, here's one.
You mean the solution, right? So the question was, does the solution work on-prem or in the cloud? Actually, both. So we do have on-prem solution and the cloud solution. It's a valid question recently. Yeah, so there are, of course, differences because, you cannot do everything on an on-prem system as in the cloud. Let's say, for example, dictionary DGA. You need to observe the queries in a long period of time. In the on-prem, you have some limits from the perspective of, cost, right? You cannot use huge amount of memory, CPU, and so on. So then you do it in the cloud, where we store the data, in passive DNS, we store it anyway. So we use it to actively search for threats just by using passive DNS data. And also we do dictionary DGA detections. Lots of also spammers actually use dictionary DGA to just generate different domain names for spam or for phishing campaigns. So not necessarily it is used by advanced attackers, sometimes also even by simple guys. Yeah.
Do we have any more questions for Piotr?
Okay, thank you.
So thank you very much to Piotr for that presentation. Thank you.